We do not know the Milky Way galaxy. Yes, even though we are in it. Before you think that I'm talking about niche details about stellar formation, how galaxies evolve, or things like that, I'm not. Even some of the basics about the Milky Way are mysteries to us, like how many stars are here? What is its basic shape? Specifically, does its spiral have 2 arms or 4? Although those might seem like simple details, we don't actually know them. Number of stars estimates range from 100 billion to as high as 400 billion, depending on what estimates are being used. Scientists have gone back and forth between 2 or 4 arms over the last 2 decades. Currently, we're leaning towards 4. This makes sense. It's naturally harder to look at a thing that you're inside. It's easier to look out your window at the house across the street than it is to look at your own house from that same position. But here's a fun one for you. How many galaxies are in the Milky Way galaxy? According to ESA's Gaia Space Telescope, which has just finished its 10-year mission, the answer is not just one. Gaia has been mapping the stars of the Milky Way, performing 3 trillion observations. And now, as it takes its final look at our galaxy, the data is being evaluated. 30,000 stars are moving a little strangely. They are going the wrong way. They are originally not from around here. I'm Alex McColgan, and you are watching Deep Astronomy. Join me today on a deep dive into Gaia's data to answer exactly how many galaxies did the Milky Way eat. As I already alluded to, looking at our own galaxy is surprisingly hard. I've mentioned before in a previous video how all of the stars, stellar clouds, and gas can actually get in the way of what we're trying to look at. This gets particularly bad towards the center of the Milky Way's plane where the most matter accumulates, creating an area astronomers refer to as the zone of avoidance. Visible light cannot easily penetrate this zone, leading scientists to resort to other mediums like X-rays to scrutinize what lies beyond. To carry on our house analogy from earlier, we are sitting in our bedroom, trying to figure out the layout of the rest of the house, but the walls right in front of us are preventing us from seeing any of the other walls and rooms. Further compounding this is a difficulty in telling how far away a star is from Earth. To make an accurate 3D map of the Milky Way galaxy, you need to know if the stars you can see are dim, small, close ones, or large, bright, distant ones that only look dim and small because of their distance. Not all stars make this easy. While some types of stars, such as Cepheid variable stars, have a predictable enough luminosity that their distance can be calculated if you know a few things about them, not all are quite as accommodating. So, for unpredictable stars, how can you tell how far away they are? The answer is parallax, and that's what Gaia has been using over the last 10 years for its galaxy map. Parallax is a principle that, depending on your viewpoint, things can appear to be in different places. You can see an example of this right now by holding up your finger in front of your face. Close one eye, then instead close the other. Now alternate quickly between the two. See? Your finger moves quite significantly in relation to its background. The closer an object is, the greater the effect of parallax. Simple trigonometry takes care of the rest, allowing you to calculate how far away an object is. While this effect was very noticeable based on a finger in front of your face, you'll see much less parallax on a tree on the other side of field, which means it's further from you. The further away something is, the harder it is to use parallax to tell you its distance. Things can get a little imprecise. But how then can we use this method to calculate the distance to a star? The secret is to widen your base viewpoint. Just as the distance between your eyes can influence the apparent parallax of an object, Gaia viewed stars not just once, but multiple times over the course of a decade. In that time, the face of our night sky will have changed, as we can see in time lapses like this one, with an exaggeration of 10,000 times rather than using the 6 centimeters between your eyes as a base. Every half a year we can make the solar system our base instead. Our Earth moves from one side of the sun to the other, which causes parallax effects to be visible in every star we see. Note how in this animation stars are taking little looping patterns? That's not really how they are moving, but how we are. That's the effect of our own loops around our sun. This can help with measuring stars' distance, but there's actually an even larger scale we can use, the proper motion of stars. We can ignore the loops for this one, as an even larger base is coming into play. Rather than just use a motion of our planet on either side of the solar system, we can make use of the fact that our own solar system, along with the other stars in the galaxy, are also moving. So, we can use that motion as an even larger base for establishing parallax. The same principle applies, Stars with larger proper motions against the backdrop of space are closer, while stars with less proper motion are further away. In this way, Gaia has been building a precise 3D map of 2 billion stars in our Milky Way galaxy and beyond, over the course of 3 trillion observations. But Gaia has not just been looking at their motion and distance. ESA's mission for this telescope was to study the luminosity, temperature, mass, and chemical composition of these stars too. It houses 2 powerful telescopes that channel light from 2 different directions into a camera with nearly 1 billion pixels, the most precise camera in space. Its radial velocity spectrometer can measure Doppler shift to give us clues about its velocity. It also has photometric instruments to reveal spectral information about each star's properties like composition and temperature. So although 2 billion stars is only a drop in the ocean of the 100 billion stars thought to inhabit the Milky Way, this still allows us to create an incredibly detailed map of our galaxy over time. And it's that over time bit that allows us to see the Milky Way's eating habits. Since 2013, when Gaia was launched, it has been collecting data which ESA scientists have been processing and releasing in large data packets for the general scientific community to study. The larger the gap in time, the more comprehensive and precise the data, more time equals more parallax. 3 such data releases have taken place so far, in 2016, 2018, and a 2-parter that released a simplified version in 2020 and then the full version in 2022, and scientists have already had the chance to evaluate what Gaia has seen. The slow accumulation of data helps us build up an incredibly detailed picture of what the Milky Way galaxy looks like. But while this is a game changer for science, it's far less comfortable when data is slowly, methodically built up about us. Give it a try. And as they witnessed the motions and locations of stars in our galaxy over time, it became possible to model the whole galaxy, and even wind it backwards. Take a look. It's impossible to photograph our own galaxy, as no camera-equipped spacecraft has traveled out that far. But here's a representation, created using Gaia's data, of what it looks like to an unprecedented degree of accuracy. Note its wobbly edges. These indicated to scientists that the Milky Way crashed into another galaxy in the distant past. Using the second data release, researchers from the Netherlands looked at 7 million stars and found that 30,000 of them were moving strangely. While most stars, including our own, move around the Milky Way in one direction, this collection was moving the opposite way. Their color and brightness were also strangely distinct, indicating there was something special about this particular group. The researchers ran the numbers and found that a model that fit their observations was what would happen if another galaxy collided with our own. The collision must have happened 8 to 11 billion years ago and involved a small dwarf galaxy that the researchers named Gaia Enceladus, or sometimes the Gaia Enceladus sausage. See how its stars, indicated here in red, actually managed to retain a fairly discrete form for a time, before eventually spreading out across the Milky Way. This merger may have been an important part of how our Milky Way came to have some of its unique characteristics, such as its bar in the center, something that only 2 or 3 RDS of spiral galaxies have. The Milky Way didn't go in for a little late-night sausage eating just once, though. Another dwarf galaxy known as Arjuna Sequoia Étoile was also found to have merged with the Milky Way and perhaps was in a binary pairing with Gaia Enceladus. Then, in a later study, another dwarf galaxy's remnants were found. More than one, in fact. According to the study, our Milky Way may have eaten as many as 6 other galaxies. Gaia data reveals this hasn't stopped. The nearby dwarf galaxy Sagittarius has collided with our own 3 times already in the past 4 to 5 billion years, and is set to do so again. This collision may even have been the spark that lit the flame of our very own sun, which came into being around that same time. Eventually, Sagittarius may well become galaxy number 7 that the Milky Way has consumed, all of its stars being slowly ripped away and brought into our own galaxy. These revelations are just some of the incredible discoveries made possible through the Gaia telescope's data, which is why it is sad that Gaia's time has come to a close. The Gaia telescope maintained a position in the second Lagrange point using judiciously applied cold gas propellant, 12 grams a day. However, that cold gas has finally run out. On the 15th of January, Gaia took its last observation and has begun the process of doing a few last calibrations before finally powering down on the 27th of March, 2025. But its story is not over yet. 2 more data packets await release. The first of the 2, Data Release 4, will include 500 terabytes of information and will be released in 2026. It will only cover the first 5.5 years of Gaia's mission, but will do so to an incredible level of detail. Its precise measurements of stars' wobbling motions might even highlight possible locations of exoplanets and will create the largest catalog of binary stars to date. It's also worth recognizing that the discoveries Gaia brought us don't end with just prior ongoing galaxy impacts. It's possible to fast-forward the data to model the motion of our local stars millions of years into the future, allowing us to see incredible models like this one. Note how, although the stars near us initially spread out across the Milky Way, they later reconvened due to what is thought to be density waves. Seeing this play out helps explain the spiral arm shape of our galaxy. Gaia data has helped improve our picture of events much closer to home, too. Gaia revealed the position and direction of travel of over 150,000 asteroids in our solar system, and thanks to its ability to track those movements over time, Gaia was able to demonstrate that 352 of them probably have moons, as shown by slight wobbles in those asteroids' trajectories. This nearly doubles the number of such binary system asteroids that we are aware of. Gaia has been called a treasure trove, and it's hard to overstate just how much information can be found in these data releases. Gaia has provided us with the largest ever 3D map of quasars across the wider universe, identifying 1.3 million of them, with the earliest being spotted at the edges of the universe, with light that started traveling when the universe was only 1.5 billion years old. Gaia has found a previously unknown black hole in our own Milky Way, 33 times the mass of the Sun, and only 2,000 light-years away from us. This type of black hole had never been seen in our galaxy before. Most local black holes are only 10 times the mass of the Sun, making this new find truly massive. Many more such discoveries can be found thanks to Gaia data. It's no surprise that ESA is already considering plans for a Gaia replacement. Gaia and IR, a space telescope similar to Gaia but able to see much further into the infrared to peer through the gas clouds that obscured Gaia's vision. But don't hold your breath on this one. If it goes ahead, Gaia and IR will look to launch in 2045 to provide an appropriate gap between that mission and Gaia. To allow ESA to take even more advantage of parallax effects, Gaia and IR will be able to see how much further Gaia's observed stars have traveled in the intervening time. When it comes out, Data Release 5 will be the big one. Tentatively set to be released by the end of the decade, this data release will include everything, all 10.5 years of Gaia's mission, to the highest level of detail imaginable. It will truly be a treasure trove of information. Just think what discoveries can be made with so much raw data to sift through. Who knows what else we will learn about our galaxy? So while Gaia's mission coming to a close is sad, the wealth of data it has collected is also very exciting. Our Milky Way galaxy might be surprisingly hard to learn about, but Gaia's data will give us the best crack at it to date. Did you find this dive into our Milky Way interesting? Would you like to know more? Let me know in the comment below, as there's plenty more we can talk about. But for now, this has been Deep Astronomy, and I'll see you next time.